Here in this video, we are solving two problems from gravitation that appeared in NEET 2024. Let's have a look at the first problem. The mass of a planet is 1/10th of the Earth. Diameter is half that of the Earth. What is the acceleration due to gravity on the planet? We shall know the relation between this small g and capital G. The gravitational force between Earth and mass m could be gmm by r square. This is when we consider mass capital M of the Earth. This is the body. The distance between them is nothing but radius of the Earth, equal to the weight of the body. So small m and capital m's can be cancelled. So the relation between small g and capital G is g equal to gm by r square. Taking on that, g dash on a different planet is m is 1/10th of mass of the Earth. Diameter is half, means radius is also half, r by 2 whole square. That is 4/10 of gm by r square. That is 0.4 times of acceleration due to gravity of the Earth. Acceleration due to gravity is 9.8. So 4 8s are 32. 4 9s are 36 and 3 39. So that's going to be 3.92 meter per second square. A simple problem. Let's have a look at the second problem that is given. The minimum energy required to launch a satellite of mass m from the surface of the Earth of mass capital M and radius capital R in a circular orbit of altitude 2r from the surface of the Earth is. He is saying that from the Earth of capital M and radius R, a satellite of mass m has to be launched. That means it shall be given some kinetic energy so that it can go to an altitude of 2r from the surface of the Earth and then it orbits around it. What is that? Kinetic energy required we need to give to this body, so that satellite, so that it can go and orbit from there in a specified orbit. So we can use conservation of energy. First of all, being in orbit, it has an orbital velocity VO equal to root of gm by r plus h. H is height from the surface, which is given as 2r in the problem. So this is root gm by 3r, orbital velocity. So it has a kinetic energy because it's orbiting half m v orbital velocity square. That is half m gm by 3r. It's not only having the kinetic energy in the orbit, it also having a potential energy. Potential energy in the orbit is minus gmm by r plus h. That is minus gmm by r plus 2r. That is minus gmm by 3r. That implies total energy of the satellite while it is orbiting is sum of potential energy and kinetic energy. Potential energy is minus gmm by 3r. Kinetic energy is gmm by 6r. 6r is the LCM, minus 2 gmm plus gmm, that is minus gmm by 6r. Now, even when it is on the surface here, it has some energy. Total energy on the surface is potential energy minus gmm by r plus kinetic energy. What we need to calculate is this kinetic energy. The minimum energy, you mean to say minimum kinetic energy required to launch the satellite. But as per the conservation of energy, total energy at 2R shall be equal to the total energy at the surface for the same satellite. That implies, as per conservation of energy minus GMM by 6R, that is this energy, equal to minus GMM by R plus kinetic energy. That implies kinetic energy equal to minus GMM by 6R plus GMM by R. 6R is the LCM, minus GMM plus 6 GMM, that is 5 GMM by 6R is the answer for the problem. So though it looks like a little lengthy for you, it's actually a simple conservation of energy. Once if you know the conservation of energy, you can simply apply and solve the problem. Thank you for watching.